Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on injection molding fundamentals. My name is Sherry Cudd, and I'm the Advertising and Marketing Manager for Chase Plastics. Thank you all for your interest in this webinar and for taking time out of your day to attend. A few quick housekeeping items before we get started. Everyone except the presenter is on mute and will be for the duration of the webinar, but if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask a question verbally, please raise your hand in the toolbar and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our latest product line card, and information on our technical engineering team in the materials section during the presentation. If you are attending live, a certificate of completion and a recording of the webinar will be emailed to you about an hour after the webinar concludes today. You will receive a separate email from Jim with a PDF of the presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to Jim, your presenter, or myself. Our entire sales and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page, and you can now register here for our next webinar scheduled for February 11th on firearm and shooting sport materials. You can now subscribe or invite your coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars by clicking the subscribe here button. Another great technical resource is the Chase the Knowledge blog on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage, and you can see some of the topics we have on there currently. In addition to our presenter, Jim Werwill, who I will introduce in just a moment, we also have Jason Merkel, Technical Manager, and Andrea Kendrick, Technical Training Engineer, on hand to answer your questions today. So at this point, I'd like to hand it over to our presenter, Jim Werwill. Jim is a Technical Development Engineer with Chase Plastics and has been with us since 2022. He received his master's in plastics engineering from University of Massachusetts Lowell and his Bachelor of Plastics Engineering Technology from Ferris State University. Many of you have had the pleasure of working with Jim through some of your toughest technical issues or application development processes. And this is his first time hosting a Chase the Knowledge webinar. So without any further ado, Jim.
Well, good afternoon, everyone. Thank you for joining us. We'd like to spend this afternoon talking a little bit about injection molding fundamentals. This is a topic near and dear to my heart. Prior to joining Chase Plastics, this is a subject that I've taught globally, and hoping I can bring a little bit of knowledge to you today. So to go over the agenda, we're going to cover the basics of the injection molding process. And then to understand how we've got to where we are today, we're going to go through the evolution of the injection unit, common molding techniques, portions of the injection molding cycle, and lastly, we're going to cover some of the key injection molding studies incorporated into the scientific molding methodology. So without further ado, let's jump in to talking about some of the basics of the machine and the process. So if we see our schematic here, this is a wire diagram of a toggle clamp injection molding machine. And just to get an idea of what the injection unit is doing here, we have our hopper system, number one. This is where our raw material is going to be fed into the machine. You may often see this with a dryer attached to it or a vacuum dryer feed system attached to this so that you have continuous dry material being fed into the hopper. From the hopper, the material enters the feed throat of the injection unit and onto the screw. This screw is a three-stage typically with a feed, transition, and metering zone. The material is conveyed onto this screw. In the rear, in the feed zone, the material stays solid and is conveyed forward and exposed to the heating bands. The material, as it's forced against the walls of the cylinder, and through the shear forces of the screw turning, we melt our material and convey it forward to the nozzle tip, number three. From there, the material is forced into the tool where it is injected, packed, and cooled until it's solidified, and then we can open the tool and eject the part. So now that we've covered those basic pieces of the injection unit, let's talk a little bit about how we've got to the configuration of the injection molding machine that we're most familiar with today. When injection molding started out, we were in single stage plunger units. This is a non-screw type machine where you have a barrel that's heated. Material is fed into this. The plunger then forces the material around a spreader, and that spreader really is where the heat comes into play. So as that material is spread around the spreader there's heater bands along the exterior, and that allows the material to soften and become molten. And then the plunger continues to feed material across that spreader and into the tool. These are the oldest configurations of molding machines as we know it. Some of the most early versions of this utilized things like a hand crank wheel to operate the plunger. From there, we started to separate the plunger and the dosing unit. So you have now two injection units, one responsible for melting and feeding the material into a secondary plunger, which controls the injection and dosing into the tool. So in this scenario, material is fed into the hopper at the top and into the first plunger and around that same spreader that we saw from the prior slide. However, instead of going directly into the tool from here, the first plunger feeds a second cylinder. This injection cylinder, once it has a sufficient shot fed into it, can then inject forward and dose material into the tool. Now, you may still find some variations of those machines out there today. Most notably, Sodic produces a screw-in plunger type machine that you can find something a little bit closer to that two-unit style here, although it's going to be a plunger and a screw. So then that leads us to the most common setup for an injection molding unit that we have today. And this incorporates the reciprocating screw. So much like the other scenarios, you're going to feed material into a hopper and through the hopper into the barrel. However, now we have a reciprocating screw that as that screw rotates, material is fed down the length, lets us build a shot in front of the screw, and then we use the screw also as a plunger by the use of a check ring or non-return assembly at the end. And then that allows us to not only plasticate with the single screw, but also to use that screw as a as an injection cylinder. What we call there is a pre-plasticizing style. The two-stage and the reciprocating screw pre-plasticize. In the single stage, you're plasticizing at the same time that you're forcing continuous material over it. The reason that we've switched to this style is there are several advantages. Melt homogeneity is a large one here. You get significantly better mixing, faster injection speeds because you're not forcing solid material through the spreader. Um, you will have some higher injection pressures, but you get better injection control and better shot weight control with pre-plasticizing units. As the industry through the 70s became tighter in profit margins because of what was happening with the petrochemicals industry, having better control of shot weight, shot size, and injection to reduce scrap became extremely important for us. So these are some of the ways the industry has adapted to drive us forward through those changes. So now that we've got a handle on the injection units, let's talk a little bit about the different molding techniques. And again, we're going to look to history to see where we started and then use that to understand where we've come and why we got here. So firstly, when we were dealing with those initial plunger style machines, we had a lot of what we would call a traditional molding process. There's no splitting of the fill, pack, and hold. Everything is done in an injection. Now, in the 70s, the folks over at RJG realized that there was advantages to splitting the injection and the packing and holding phase. So the decoupled terminology comes from that group. And you will see here decoupled 1, decoupled 2, and decoupled 3. So really, this is now decoupling the injection phase from the packing phase, and then all the way down to separating a fill, a pack, and a hold stage all into their own portions of the cycle. The fill phase being injection in being velocity controlled, the pack being pressure controlled, and then hold also being pressure controlled, but you drop all velocity component. So let's unpack these a little bit so we can better understand some of their pros and cons and better understand why we have taken steps forward from what we would consider the traditional molding style. So the traditional molding process, again, this is our earliest injection technique, unsophisticated machines, single stage plunger. And all we're doing is continuously forcing and squeezing material through that heated spreader and holding it in there until the part's solidified, or forcing it in there until the part's solidified. If you didn't fill out your cavity, your only recourse is to squeeze more material in harder. However, that also led to quite a bit of what we consider overfilling or overpacking. You may see things like flash or dieseling, and those were really your only two knobs. Push it harder, push it softer. It didn't give much control at all, and certainly could not handle a lot of the sophisticated geometry nearly as well as the scenarios and the techniques that we use now. So this stage is a single stage, no splitting of the fill, pack, and hold, and pressure and time are your only controls. So then we move into the decoupled 1 scenario. This is the earliest adaptation of it, and it requires a 2-stage reciprocating screw machine or newer to accomplish. In this process now, we are filling the mold with a controlled velocity until the part is volumetrically full, and then we transfer to the pack and hold. In this scenario, the melt inertia from fill and the pressure generated is used to pack the mold. It's not a fully separated decoupled two process where the fill and pack are handled completely separately, um, but it's more the first acknowledgement that the packing of the mold was also a critical portion of the cycle. So this is a two-stage process, and fill is decoupled from a single pack hold combined step. And now you have a velocity, a pressure, and a time as your control variables. From there, we moved into decoupled two. So this is the next evolution. Again, this needs a two-stage reciprocating screw machine or newer. And now we're filling the mold under a high velocity to take advantage of shear thinning in material rheology, polymer rheology. However, unlike decoupled one, we are now underfilling the cavity on purpose in the fill stage. We're only going to fill it to 95 to 98% full so that we don't have the inertia and the generated pressure of the material reaching full volume of the cavity, but instead we're going to fill it to that 95 to 98, and then we're going to initiate a pack under pressure control. So this technique then allows us to fill much more rapidly because we don't have to worry about the inertial overshoot of filling the cavity because we're purposely going to leave the cavity with a small amount of volume in it so that we can account for that under the pack phase. So that fully lets us take advantage then of polymer rheology in shear thinning to increase repeatability. And then we can pack separately. So again, this is a two-stage process. And now fill is completely decoupled from pack and hold. And again, velocity, pressure, and time are our control variables here. From there, we moved into the decoupled three, which is what we considered the newest evolution of decoupled molding and does require some extra equipment and typically newer molding machines to accomplish. So much like decoupled two, we're going to fill the cavity under high velocity to take advantage of that material rheology and shear thinning. We're then going to pack at a low and controlled velocity to meet a set pressure. Once that pressure is generated, we can drop the velocity component so we're no longer moving the screw, but we're statically holding at a pressure now. What this does is gives us significant control over the pressure in the cavity of the tool. Now you may ask, when would that be extremely critical? High volume multi-cavitation tools can benefit greatly from a decoupled three process, but so can insert molds, especially if the inserts are delicate and have a maximum pressure that they can tolerate during the molding process without being damaged. So you may see magnets inserted using a decoupled three process to protect the magnet. If you have any sort of chip or any sort of instrumentation that you're going to be overmolding, those inserts can only take so much pressure. And if we were to go under a traditional decoupled two, we might overpressurize the cavity and start running into rejections due to destroyed inserts. So the decoupled three process then gives us full control of the amount of pressure in the cavity during the packing and holding phase. And in order to achieve this, we're going to need something in the tool to give us feedback on that pressure. So this is going to typically it's going to require you to have cavity pressure transducers in the injection mold to capture and read that pressure, so that you can then fully decouple the pack and hold phase and hold at a static pressure. This gives you an extremely repeatable process, even more so than the decoupled 2. Decoupled 2 is the predominant process used across the world today, and then decoupled 3 is gaining a fair bit of adoption depending on the style of molding and the delicacy of things like inserts. Okay, let's talk a little bit then about the cycle. So here you have a typical injection molding cycle represented kind of in a pie chart. We're looking at cycle start, mold close, filling the tool, pack, hold, cooling and recovery, mold open, and ejection. So during the fill stage, as I mentioned earlier, this should be controlled by velocity, which means we need to give our machine enough pressure to achieve the set velocity. And we need to give it a little bit extra to account for material variation from lot to lot, so that we don't end up in what we call a pressure limited situation where our velocity becomes limited by the pressure well that we've allowed the machine to use. There are a couple studies that need to be conducted during this time, and we'll talk a little bit more about them later, in order to optimize this process in the scientific molding methodology. And so in this portion of the cycle, we conduct what's called a short shot study and an in-mold rheology study. So the short shot study, this lets us determine the appropriate volume to inject into the tool to hit that 95 to 98% so that we can transfer to pack. So in order to do this, we're going to make sure that pack and hold is zeroed out or turned off. No pack and holding pressure, no pack and holding time. We're going to adjust our transfer position upwards so that we do in fact achieve a short shot. We're going to mold that short shot. We're going to weigh it and label it, part only. And then we're going to decrease the transfer position and we're going to reiterate that same process. Shoot, label, weigh at varying percentages of fill. I like to do this at 10, 20, 30, 40, 50, 60, 70, 80, 90, 95 or 98, and 100%, so that you have a significant fill progression. This lets you visualize how the tool is filling. It lets you validate your filling simulation. Am I seeing the same fill pattern on in my tool as I am in my simulation? That gives me good confidence that some of the other outputs from my simulation are likely correct, or at least directionally correct. So once we've made those 10 or 11 pieces, we can then get an idea of where our 95 to 98% fill is so that we can adjust our shot size accordingly. So not only are we going to learn how the tool fills, where gas might get entrapped, where we might need to vent, we're going to validate our simulation, and we're also then going to determine our first stage fill volume, all with this study. From there, we're going to perform a rheology curve. This is also called in-mold rheology. This is also called a in-mold viscosity curve. But what we're essentially doing is getting a relative viscosity and relative shear rate so that we can capture the shear thinning of the material in our specific machine and tool. So how do we conduct this? So we're going to turn off that second stage again. We're going to ensure that at our highest velocity, we still have a short shot so that we don't accidentally inertially overfill the cavity and flash it. So you're going to start with a high velocity and a higher transfer position so that you're not accidentally flashing the tool. So we might want to bring that transfer down a little bit from our 95, 98, maybe 85, 90%, somewhere in that ballpark, and then adjust our velocity up. We're going to make sure that we're documenting the speed, the time, and the transfer pressure at each iteration. We're going to conduct a series 2 to 3 injections at each velocity set point and document the speed, the time, and the pressure. From there, we can calculate an apparent shear rate, which is going to be 1 over the fill time. And then we can calculate an apparent viscosity, which is going to be the injection pressure times the apparent viscosity. We're going to plot those on a graph where the relative viscosity goes on the y-axis and the relative shear rate goes on the x-axis. What we should see then is a curve that looks similar to this, where at the lowest velocities, we are at the highest viscosity because of chain entanglement. And as we drive higher shear rates, we will drive higher degrees of shear thinning in the material, which will drive down the viscosity. So then we should be able to find a point once this is leveled out where we have repeatable velocity for our process. And we can look at this, and if we come back up the curve and say we were to pick a shear rate somewhere in this region, okay, and we had a small change to the shear rate. Well, that small change to the shear rate due to material variation, due to process variation, would kick our viscosity up a significant amount. If we're processing over here where the curve flattens out, you can see that a small change to the shear rate leads to a relatively negligible change in the viscosity. That's where we want to end up processing from a repeatability standpoint. So I've been mentioning taking advantage of the shear thinning behavior. So what is this? So when plastics are exposed to shear, like I said, we get an untangling. So at solid, you have just an entangled mass of polymer chains. As we heat them, those chains start to increase their intermolecular spacing. So you can think about this like the chains getting a little further apart. Once they're hot enough to be far enough apart that we can slip them past one another, we have flow. As we flow them at higher rates, we get orientation and alignment. That orientation and alignment is what drives our viscosity down. That's what makes a polymer a shear thinning material. So another way to think about this is polymers are non-Newtonian. A Newtonian response would be a linear response between shear rate and viscosity, while a non-Newtonian is a nonlinear response. So we can see here, these are several different standard polymers, ABS, polycarb, nylon 6, and we're showing 4 different what we call shear rate regimes. So very low shear rates for compression, molding, and calendaring, a little bit higher shear rates, and this is a logarithmic scale for note, a little bit higher shear rates in extrusion. Injection molding, we have middling shear rates, and then in fiber spinning, we have high shear rates. So what we're really interested in is the polymer's response across the shear regime that we're going to be working it in. So for today's conversation and the purposes of this webinar, we're going to be talking about this middling shear regime where we do our molding. And we can see that the response of these polymers is not linear in this shear regime. And that's why we do the in-mold rheology study. Um, and this is really what we're trying to understand when we're doing that shear sweep and trying to figure out where we should best process these materials. Okay, so once we've filled the tool to our 95 to 98, we transfer from velocity control to pressure control. Many people call this transfer. Others will know this as the VP switchover position. That VP literally means velocity to pressure switch position. So we're switching our control methodology between fill and pack and hold. It's extremely critical that we transfer at the correct position. If we transfer too early, we will likely underpack parts. If our packing velocity is lower than our fill velocity, we may see things like record grooving or hesitation banding appear on our parts. We might short shot. We might also drive a high amount of stress as we're getting a frozen layer building as we're trying to drive that polymer at a slower speed than through a constantly decaying flow bore. On the other hand, if we transfer too late, we can flash the cavity, or we can diesel, or we can mold in a very high amount of molded in stress and residual stress, which will result in the part likely failing prematurely under load in application. So getting this position correct is extremely critical to the performance, repeatability, and quality of the molded product. There's a couple methods that we can do this, and we've got them listed. These are your standard, most common 4 methods to transfer. Most of your machines will at least give you the top 3 as a standard drop-down menu to select from. And we do have them here in order of accuracy, where transferring by time is not as good as transferring by pressure, which is not as good as transferring by position, which is not as good as transferring by cavity pressure in terms of shot-to-shot repeatability. So let's talk about each of these just a little bit. So if we transfer by time, our screw is going to inject forward for a set duration. It's very easy to set this up. However, we don't then have any feedback on how much volume went into the cavity. There's no direct tie to amount of plastic going into the cavity and the transfer position here. It's strictly inject for this amount of time. Now, if there's some changes, because injection molding is not a steady state process, it's a pseudo steady state, we're going to see some heating and cooling transiently as we're going through our run that can lead to some slight changes in viscosity. Same thing, batch to batch, lot to lot of resins, setup to setup, we might see some small changes. Transferring by time does not account for this. It will let you maintain the cycle time, but it will not as accurately let you maintain a volume of plastic going into the cavity. So another way we can do this then, a little bit better, is by giving some feedback and doing by pressure. Once the screw reaches a set pressure, then we're going to transfer over to pressure control. Again, though, this is not directly tied to volume, but tied to pressure. So if our melt temperature changes a little bit, if our molecular weight changes a little bit, our transfer is now changing. And we are changing the volume of material that we're putting into the cavity. Okay, so if we take that, we can take that a step further to position. So now we're going to say inject forward until you hit a linear position of the screw. which then gives us some variable injection time. However, it will give us consistent injection volume into the cavity. So this is the most common transfer trigger used in the industry today, is position. And it's the most accurate trigger that your machine will come standard or as a standard option on your machine. If you have transducers in your cavity because you intend to do something like a decoupled 3 process, you can also use the signal from those transducers to transfer from fill to pack. You will typically have a transducer near the end of fill, and when the transducer starts picking up pressure, you know that the melt has reached that point in the cavity, and you can transfer over to pack from there. That allows you to transfer consistently at the same cavity pressure. That is also an extremely successful method for triggering transfer and offers a high degree of repeatability, but does require those transducers to be able to pull that off or to be able to accomplish that method. So now that we've talked about triggering pack and hold, let's get into that just a little bit. So pack, this is the second stage of the molding process when the part finishes filling that remaining 2 to 5%. We still need to put volume into the cavity during the pack phase, not only to account for the change in density through solidification, but also note that we are injecting to 95 to 98% under fill, so we have to take up that other 2 to 5% under pack, and then a little bit more to account for that densification during solidification. Now, because we're still putting volume into the cavity in pack, we still have a velocity component to that piece of the puzzle. Pressure is the control variable, but the screw is still moving forward. Many new molding machines will give you control of that velocity for your pack. What differentiates pack from hold is hold drops its velocity component. Now, once we've generated a set pressure in packing, because we're still driving that screw forward to generate that pressure, as soon as we hit the set pressure there, or desired pressure, we can stop the velocity component and hold the screw static at a given pressure. This lets us keep everything in the tool. If we were to release pressure at that point in time without having a gate sealed off, you can get backflow out of the cavity, which will then introduce some quality issues. So pack and hold are typically pressure and time controlled. Pack has a velocity component and is pressure controlled. Hold is pressure controlled with no velocity component. So cushion, a packing pressure study, and a gate seal study are the scientific molding steps that can be done now in this phase. So it's so important to have a cushion. I just want to talk about it quickly. It's not a study that we necessarily need to do. We like to dial in the cushion so that we get somewhere between 1/8 and 1/4 inch of material left in front of our screw to pack off of, or to use for packing at the end of our cycle. So we should end packing and holding with about that much molten material left in front of the screw, 1/4 to 1/8 of an inch. The cushion is absolutely necessary because of fluid dynamics. In order to pressurize the molten material in the cavity, we have to be able to act on that through a connective molten pathway. So if there's polymer, molten polymer in front of our screw, we can push on that and we can transfer that pressure all the way into the cavity. If our screw bottoms out and cannot push on molten polymer on the cushion, we lose our ability to pack because we cannot pressurize the cavity. So we have to have cushion. It's what's left over once we're done packing and holding in front of the screw. But if you don't have it, you've lost control unless you're doing a foaming process. We're not going to talk about that today, but that's one of the few exceptions. So from there, we need to figure out how much pressure to pack with, and then we need to figure out how long to pack for so that we can seal off. So how hard do we pack, how much pressure we use is directly related to sinks, voids, and then flash. So we want to establish our 95 to 98% full. We're going to set our packing time high, typically around 10 to 15 seconds. That should give us some approximation of a gate freeze. We're going to start with a low pressure, and we're going to mold a part with a low packing pressure for 10 to 15 seconds. That should produce us a short shot. And then we're going to incrementally increase that pressure until we have an acceptable part with no shorts, no sinks, no voids, or at least an acceptable amount of sink or void. That will be our minimum pressure. We're going to document that. That is the bottom of the window. We're going to continue to incrementally increase that pressure until we no longer make acceptable parts, either dimensionally out of tolerance on weight, or we start flashing, angel hair flashing the cavity, which is just the first onset of parting line flash is what we call angel hair flash. It's very thin, very wispy. It's not a gross flashing of the cavity. It's just a small line that starts on the parting line. So as soon as we've hit that point, that's the top of our window. Weigh and label, and then we're going to select a packing pressure in that window. Could be 50%, could be 75%. The less pressure you use within the window, the less stress and energy you're using. So you may want to shade towards maybe 25%, the bottom quarter of the window. But regardless, you now have a window that you can pack within and produce good parts. The wider this window, the more robust of a process. The narrower this window, the tighter the process. So once we've established that pressure, we then need to establish a time. We need to hold the material in the cavity until the gate solidifies so that material cannot backflow out when we remove pressure from the screw. So we are going to use that ideal packing pressure that we found from the prior study. Now we're going to take that 10 to 15 second time that we had and we're going to zero that. And then we're going to start incrementally adding packing time each shot. And we might go 2 or 3 shots per time setting to let the machine stabilize and the process stabilize. And we're going to weigh the parts, not the runners and the gates. We're going to remove those and we're going to weigh the parts. We're going to plot that part weight as a function of packing time. And what we should see is an increase in weight until an asymptotic point where we're no longer able to pack more material into the cavity. This is a very good indication that our gate has frozen, and at that time, we can no longer affect what's in the tool with the screw and through packing and holding pressure. At that point in time, we might want to give a small buffer for material variation, and then we're going to use that as our packing time. So our freeze time plus a small buffer, and we're going to then set that as our packing time. That's going to ensure that every cycle we freeze the gate and that we have a consistent amount of material that stays in the cavity. From there, the cooling timer will start. Once pack and hold is done, we start cooling. Cooling and recovery, screw recovery, building the next shot happen concurrently. You oftentimes may use a delay before recovering the screw so that the material isn't sitting at molten temperature for longer than necessary. However, there is one thing to note and to think about. The second the material is forced up against the mold wall in the pack and holding phase, we have technically started cooling. So, if you need to pack for longer to account for sinks or voids, and say you needed to add 3 or 4 seconds to this pack and hold, you can effectively also take that off of the cooling and still have the same amount of technical cooling time. Just because the timer for cooling isn't running at that point, we know that as soon as we are pushed up against mold wall in pack and hold, we are effectively started our cooling. So that's a little nuance to keep in mind. And then we're going to recover that screw a second or two before cooling time times out. Mold will open, part will eject. We'll go again. Now, we can notice from this pie chart as well that cooling is the largest portion of the injection molding cycle. And this is because polymers typically have low thermal diffusivity, meaning the rate of heat transfer from the polymer to the mold is slow. And it slows down over time as we're solidifying and as an air gap starts to form as we shrink away from the cavity surface. So there's a lot of variables that will affect that cooling time. Thickness, melt temperature, mold temperature, injection rate, packing time, mold design. This is a PVT relationship, pressure, volume, temperature. And you will typically see this around 30 seconds or under. For thick wall parts, that might get up into the minutes, just depending on your specific geometry and scenario. And at that, I'd like to say thank you for your time. I'd like to thank Sherry, Jason, and Andrea for their support. And I'd like to open the floor to any questions.
Awesome. Thank you, Jim, for your comprehensive presentation. So as Jim said, at this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. As Jim mentioned, we do have Jason Merkel, Technical Manager, and Andrea Kendrick, Technical Training Engineer, on hand to assist Jim with questions today. So as you're typing your questions, as a reminder, please remember to complete the survey at the end of the webinar. Your responses will shape future Chase the Knowledge webinars, and we always welcome your feedback. Also, please be sure to check out our blog page at chaseplastics.com/blogs, and you can access past webinar recordings and future webinar announcements and registration at chaseplastics.com/webinars. If you'd like to have a custom Chase the Knowledge topic presented to your organization exclusively, please reach out to Jim or myself and we can get that set up for you. So Jason, I will leave you and Andrea to the questions.
Sounds good. Thanks,
We have
Sherry.
quite a few.
All right, Jim. First question is, what would be an ideal starting injection speed for conducting a rheology study, considering factors like material viscosity, shear rate sensitivity, and the machine's max injection speed?
That's a really good question. Now, we like to start at that higher velocity so that we don't end up increasing along the way and flashing the tool. Honestly, a couple hundred millimeters per second, or call it 4 inches or so per second, 6 inches. You can go pretty high here, as long as you're not going to. And this is why we set that shot size lower, so that we don't inertially flash, because you're not going to fill the cavity during this fast injection. You actually have a little bit more safety. If there are features of the tool that are delicate, slides, standing cores, things like that, we might want to truncate that speed down a little bit. but you can run this pretty high. 75% or so of machine capability is not out of the realm of possibility as a starting point. Monitor your pressure as well. If given the gate size and things like that, you're maxing your injection pressure at those speeds, bring that down a little bit because you will not have process window to consistently be at that injection velocity. So it's a nuanced answer. You do want to start as high as your process or as your machine and gate size and such will allow you, and then work backwards. And that's oftentimes going to be 75%, 80% of machine maximum.
Awesome. Thanks, Jim. Next question, not so much for the content necessarily, but question, I think it was given it. But just for anyone else curious on the call, the question was asked if we're going to be able to share this video. Short answer is yes, it will be available on our website, chaseplastics.com, under the resources tab, and then also available on YouTube should you prefer to view it there as well. Next question, have you ever dealt with any straight rubber molds?
So injecting thermosets is a little bit different of an animal. I've done some of it. It's been since grad school days, to be perfectly honest. It's a different process setup in terms of unvulcanized, uncured, your viscosity starts very low. You don't have the same shear thinning effects that thermoplastics have because of chain length. So yes, we've done it. We've got a couple people on our team that have done some of that work. It is a different setup. It's not something that we necessarily specialize in, but if you wanted to reach out with a more specific question on an issue you might be facing, please feel free to shoot me an email.
Thanks, Jim. A few more here. Just a question, if you could reiterate how do you determine when you have gate freeze? I don't know if you want to toggle back to that slide maybe first.
Yeah, let me jump back up to that slide. So can we see the curve we've got going on over here?
Yes.
Okay, so if we look at part weight is going to be on the Y, impact time is going to be on the X. And now again, we need to singulate these off of the runner in gate, because even though the gate is frozen, our runner is not, and we can still pack that runner out and artificially change this curve. But what we'll look at is that part weight will consistently climb until our gate is frozen. So what we see here is our gate's still not frozen here because we were able to add a 1/10 of a gram, another 1/10 of a gram, gate's still not frozen. We're packing it 2.5 seconds now. We can still get another 1/10 of a gram in there. Part weight is still increasing. That means that flow channel, the gate, is still molten and open. You'll notice at about 4.5 seconds here on this particular curve, we can no longer affect the part weight with more packing time. That's a great indication that that gate is solidified because we can no longer adjust what's happening past it. If you have cavity transducers, like you're doing a decoupled 3, what you will also see if you have a gate transducer or a cavity transducer right at your gate is the pressure will decay off of that because the gate is solidifying and shrinking away from the transducer. So also when that cavity transducer at your gate starts to read 0 pressure, you can also infer gate freeze from that. We will have a template here after for your use. So what you're just going to do in that is you're going to mold the part with 1 pack time, weigh the part, keep going up, put it right into the workbook that we're going to send you, and it's going to generate this curve for you, and you're going to look for that curve to flatline. Once that curve is flatlined, my gate's frozen.
Awesome. Thanks, Jim. Got a positive response on that by the question asker as well. So thank you. Last question for now. Is it better to have liquid plastic flow in from underneath the cavity or above it?
So I think you're maybe asking, should the orientation of my mold in the molding machine? So when we look at all of the equations that we use to model polymer flow, and I'm talking Navier-Stokes equations, if you look at like fundamentals of polymer processing from Tadmor and Gogos goes into this ad nauseum. But what we find is that the viscosity component far outweighs gravity. So it oftentimes does not matter if you're injecting down or up, because the viscosity is going to dominate gravitational effects. There are some caveats to that. Very low molecular weight materials that flow very easily at temperature might show some gravitational effects, and you might benefit from injecting up. Very thick wall elastomerics running at hot temperatures, you can also see some interesting things that can occur from injecting against gravity. Or you can improve some of your repeatability by injecting against gravity. You will also see this in particle injection molding, ceramics and metals, because the binder that's used to carry the ceramic powder or the metallic powder is extremely low molecular weight compared to most polymerics that we would mold and form a final part out of. Those do not have the viscosity necessary to dominate gravity. And a lot of times we are going to inject those up and against gravity. But in most of the scenarios that you will come across in your lifetime, viscosity dominates gravity.
Next question, I believe, plays off that same question, Jim. Does venting come into play?
Oh, yes. Venting is an absolutely critical portion of this, because entrapped gases will work against, will increase your cavity pressure. So we can artificially reduce robustness of process window if we can't escape gases. We will run into periodic dieseling issues, short shotting, and things like that if we don't have adequate venting. A good rule of thumb is you don't have enough venting. I know that's a little bit flippant, but when we're simulating this, say with a mold flow or a Moldex or things like that, we're assuming perfect venting. So as close to that as you can humanly possibly, or as close to that as you can get with limitations is really where you want to drive. Um, and like I said, you can artificially truncate the robustness of your process window or the width of your process window with inadequate venting.
A few more here that are trickling in. Are there any tests or techniques to determine mold temps?
Sure. Really, you can look at this in a couple ways. If you are in a semi-crystalline material, your mold temperature needs to be above the Tg of the material, or else you will not fully develop crystallinity during the solidification and cooling process, which will lead to a reduction in mechanical properties compared to datasheet. So, rule of thumb for semi-crystalline materials, you've got to be above Tg, and it's usually a handful of degrees above Tg to maintain molecular motion so that they can, in fact, get to their crystalline morphology during cooling. Amorphous material is a little bit different. We're looking more at VICAT and HDT in those scenarios, where you just need to be cool enough to not deform or punch pins through the part upon ejection. You can also do some things with locking in molded in stress by cooling too quickly and too aggressively, and you can then artificially inflate your cycle time by not cooling aggressively enough. So really, you can do especially in an amorphous material, you can look at running a study where you're changing the tool temperature, the steel temperature, taking a physical measurement. I'm less concerned with what your thermolator is set to versus what your steel is actually giving you. And then you can look at the pin push and part deformation upon ejection as a function of those mold temperatures. Now, like I said, though, in a semi-crystalline, you can do that too, but the caveat there is you have to be above TG. Hope that helps.
Oh,
Absolutely. I think that's the rest of the questions, if I see correctly, Sherry.
yeah, I think I saw a hand up. Mario, if I think that was who had his hand up. If you have a question and want to speak your question, just raise your hand and I'll go ahead and unmute you now and you can ask your question. Maybe it was answered. Okay, it is Mario. Mario, I'm gonna unmute you.
Can you hear me?
We can hear
Sure
you.
can.
My question was for family molds, where you have cavities that are of different orientation and different sizes. And is it possible to apply a decoupled two process to a family mold with the same type of material?
Yes, but. So thank you so much for asking this question. This is a great line to go down. I'm going to state this personally. My personal bias is I don't love family tools. Um, and the reason here is if you have any dissimilarity in volume, you're going to run into one of two scenarios. So either you're going to go hydrostatic and overpressurize a cavity, or your one cavity is going to be significantly behind in terms of the volume or the velocity it was filled at, and ultimately the melt temperature in the cavity. So, what you do for a family tool is you have to optimize for first to fill. So, instead of using the 95 to 98 on your single part or on your same geometry across the board, you apply that to your first to fill cavity.
Valve
But that
gates, maybe a
valve
valve gate.
gates. So valve
Okay,
gates are an entirely different animal there as well because you don't have to freeze that gate. You're going to artificially or you're going to mechanically close that gate.
oh, gotcha.
So that now you're looking at part weight, flash, voids, and sinks. So as soon
Okay,
as you have a part that is acceptable weight and acceptable quality, you can close them gates down. And then the valve pin itself is going to prevent the backflow.
okay. So it does have its challenges to get to apply a decoupled two process, but okay, that
Family
answers.
molds are one of the more difficult just because of the dissimilarity in volumes. And you can play games with balancing runners and choking things down, speeding things up, but do know that your runners having those different runner sizes are going to change the amount of shear heating in each of those legs of the runner, which are still going to then result in slightly different molded in properties.
Okay. Makes total sense. Okay. Well, thank you so much. I appreciate you answering that.
I appreciate your question, Mario. Thank you.
Yes, sir.
Jason, looks like we may have just had another question pop up there. If you want to
Yeah,
take it.
along a similar thread, Jim. First of all, kudos to you. You said nice work. Can you please talk about gate sizing with family molds to obtain 95 to 98% fill? So maybe similar answer to
Yeah,
what
so
you
I
just.
started to get there, right? It's
Mhm.
it's less gate sizing and more runner leg sizing to balance those. So you'd be trying to account for the differences in volume with the runner sizing. But again, like I said, that creates its own problems. John Beaumont and his group did a lot of work to determine that shear imbalance is in fact a true phenomenon, and that's all generated from shear heating through your runner system. So if we take that to be true, that we can have balance issues based just on shear heating and whether or not we're inner bends or outer bends on a runner branch, then that same theory would apply to different sizes in our runner. So we would expect to see some differences in shear heating and things like that down those legs. I think you're better off doing some iterative work on fill simulation to try and balance those. But from there, if you have two wildly different gate sizes and you're then doing your gate freeze study, you have to pack. So when you're doing your how much volume, you use your first to fill. When you're doing how long do I pack for, you're doing your last to freeze. That's the only way you can ensure that all of those cavities are at freeze off. You're going to make some really pretty runner systems for the cavities that freeze off first, but you have to do it that way, or else you're going to have backflow out of the gates that freeze last.
The further to that question, same asker, to further elaborate, if you can't change the runner size, would adjusting the gate size after T1 trials allow for that? I guess similar fill.
You can. So again, you make that gate a little bit bigger so that it biases some flow through it. You can pack it out longer. It's no matter what you do in a family tool, you're inviting some variation just by the fact that you have a family tool and you're going to have to pick a poison. So it's just almost too nuanced at that point. If there's some specific scenarios that you would like to talk through, call me, give me an email. Let's talk through that specific scenario on how best to balance that without sacrificing um, too much part performance. I'd be happy to do that. But there's always going to be a sacrifice in a family tool. You're saving cost, you're sacrificing performance.
Awesome. Looks like the last question for now. What is the pressure for the fill stage test?
So, in your fill stage, pressure is a well. You're telling your machine you have X amount of pressure to keep the screw moving at this velocity. What you're going to want to do is when you're first setting up this process, you're going to set that to maximum. You're going to give the machine all she's got, all they've got, all it's got from a pressure well perspective. Okay, so you're going to put that injection pressure to maximum. Over the course of your work, you're going to get to a stable process and you should get to a relatively consistent peak injection pressure. From there, you're going to dial down your set point to be a buffer above what your consistent peak injection pressure is. So say you're consistently hitting 14,000 psi peak injection. I might give myself 10% and set that, at 1550 or 1540 or so, just so that I can account for some shot to shot variation, but I'm not allowing my machine to go to full pressure if something freezes off or doesn't eject out or something along those lines. So that's what we typically do to ensure operator safety, but still give the machine as much pressure as needed to ensure robustness and repeatability.
All right, I think that concludes our questions. Jason, do you see any that I'm not seeing out there? But I think that's all of
I
them.
believe you're correct. Yep.
All right. Well, we would like to thank you all for taking time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Jim directly. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar in February. And happy holidays, everybody. Stay safe out there.